of processor, but the instructions are of various length. So here all the instructions are of same length. They are of 32 bits. And in this 32-bit instruction, 8-bit will be kept for opcode, and that means 24 bits will be for operand. As you know that instructions are of two fields mainly here. Like you can see the opcode and the operand field. So operand field is 24 bits and opcode field is 8 bits. In this 8 bit, the most significant bit is kept for type of the instruction, in the sense like whether analog or digital. Say if it is if the most significant bit is 0, then let's say it is the instruction is analog digital, or if it is 1, then it is for analog or vice versa. So that means this most significant bit out of these 8 bits are reserved for determining whether it is an analog instruction or digital instruction. In the normal microprocessor, we have not encountered this kind of situation because all the instructions are digital. But since it is an AD processor, here this provision has been kept. Okay. So now, operand field to be not 26 bit, 24 bits. So 24 plus 8. And since it is a RISC architecture, the basic philosophy of the RISC processor is that program memory and data memory will be separate. Okay, that means programs will be stored in the program memory and data will be stored in the data memory. Since here the data is of analog type and digital type, so there will be separate digital data memory and analog data memory. So altogether there are 3 types of memory: digital data memory, analog data memory, and program memory. Because program memory is same for whether it's an analog instruction or digital instructions. They will be stored in the instruction format. Automatically there will be 5 buses. Okay. Like for digital data memory or analog data memory, there's the digital address bus, program memory. So program memory address bus, program memory data bus, and right like that. So first is what are the 5 buses? Program memory address bus, program memory data bus. So in the program memory, if the address is given, then the instruction will be coming. Digital or analog data memory address bus, digital data memory data bus, and analog data memory data lines. Here for analog we are not calling it bus because bus consists of a number of lines. Each line carry 1 bit, like 0 and 1, but for analog a single line which will contain the data. So that's why we don't call it bus, we call it line. And address data and control signals are different. Because for each memory, read and write, these are the control signals have to be given. And there must be provision for pipelining, because the RISC architectures are pipeline-based architecture. And RISC architectures, they employ large number of registers. Okay. So here we have 32 registers, each of 32 bits. So data size is 32 bits. Now up to that, is there any doubt or anything?
No, sir.
No, sir.
Fine. So this is the structure of the instructions, opcode and the operand, as I have mentioned already. And opcode 8 bit, out of that 1 bit is for this. So what is the program memory size? So program memory size will be like each instruction length is 32 bit and address size will be what? Since 24-bit address lines, okay, that means the size of the address bus. So total number of locations will be 2 to the power 24, and each location consists of 32 bit. So program memory size is 2 to the power 24 into 32 bits. That is equal to 16 mega into 32 bits. Okay, 16 mega words where each word is of 32 bits. Digital data memory size will be same, 2 to the power 24, 32 bit. Analog data memory size will be 2 to the power 24 into one sample. In each location there will be one sample. Okay, because why I am calling it one sample? Because how the analog data will be stored in the memory. Analog data will be sampled because analog signal will last for a time, finite amount of time. You cannot store like that, so you have to store each sample. Okay, so that's why we call it 16 mega samples. That is a storage area. Excuse me, for analog memory. So maximum number of digital instruction, how many? Since out of 8 bits, 1 bit is for type, so left number of bits left is 7 bits. So 7 bits. So how many instruction? 2 to the power 7. So maximum analog instruction is 2 to the power 7 equal to 128. And so analog and digital instruction, it should be 128. It's fairly less. Now, how we are defining the addressing modes? Now, we have kept, for the simplicity here, we have kept 4 addressing modes. Direct memory addressing means within the instruction, the address of the memory will be given and memory can be accessed. Memory access means either data could be written onto the memory or data could be read from the memory. Only the indirect memory addressing, that is, the address will be stored in some register. So some register will hold the contents of the address. Like your in Intel 8085, you have HL register, which holds the address. Immediate addressing means within the instruction, the data will be given. And another is the register addressing. So register addressing is transfer the data from one register to another register, and so on. Okay. Now, type of the instructions are digital or analog data transfer, digital arithmetic, digital logical, because logical instructions cannot be for analog, it's for digital only, so digital logical, then analog arithmetic, digital data manipulation instructions. Data manipulations are like shift left, shift right, rotate left, rotate right, etc. Okay. Rotate with carry. Then the branch instructions. Branch could be conditional without unconditional. Okay. So unconditional is simply branch to some address. Conditional like jump on carry or jump on negative, etc. Jump on 0. Then subroutines like call instructions, call to some address, and when it will be over, then it will come back. And whenever there is a call instruction, there must be a return instruction. That also falls under subroutine, because otherwise it cannot come back. Then there must be stack pointer, which must have to be loaded, and machine control. Machine control means the way to stop the machine, like halt instruction. So to see that these instructions, 4 addressing modes, 8 instructions. So you can say that this opcode field, which is 8 bits, so 1 bit would be kept for type of the instruction like analog or digital type. 2 bits are kept for addressing mode because since there are 4 addressing. 3 bits for type of instructions because there are 8 types of instructions. So 3 bits will be required. 2 to the 3 equal to 8. So how many bits are left in the opcode? 3 to 5, 1, 6, only 2. So 2 bits are for actual operation to be performed. Okay. I can give you one task. Okay, Arijit, you do one thing. Just I'm trying to make this table. Can you see the table?
Yes, sir.
Okay. I've done 1 or 2. Rest you can do. Then you will understand it more clearly. I have made a table. In the table, there are 5 columns: type, direct, indirect, immediate, and register. These are the addressing mode. And instructions type are data transfer, digital arithmetic, digital logical. Because analog logical is not possible. So analog arithmetic, then digital data manipulations. Analog data manipulation is not possible. Because or this kind of operations will be done only on the digital data, not on the analog. And then branch is the same for both of them, subroutine and machine control. Now here for direct data transfer. Data transfer means what? Data to be transferred to the memory or from the memory and so on. So I've just written here one instruction. There could be in each type, in the extreme left hand column, under that there could be 4 instructions. Isn't it? So 4 instructions for each of this mode. So data transfer is load, digital or analog, whatever it is, memory address. The instruction is like, let's say the memory of the instruction is LDA, DA. So LDA D or LDA A, whatever it is, doesn't matter. So here you have to give the memory address. So LDA D means load accumulator, the digital instructions from the memory address, so and so. Simple. Or load AA means load accumulator in the analog with the analog data and memory address, analog memory address is given. Similarly, indirect is there. Load accumulator indirectly with here the register will be given. Similarly, load immediately. The data itself will be there. And register addressing is load RI RJ. That means data will be loaded into RI from RJ. Here we are following the Intel convention where the right hand side data will be stored into left hand side data. Similarly so under each type and each addressing mode there could be 4 such instructions. So load A contemporary will be stored. So for indirect, load A indirect, store A indirect. In that way you can do all this. Okay. So rest of the things I suggest you to complete the instruction set. And next day when you will come, you can show me. So then it will be easier for
Okay,
you.
sir.
Okay. Because instead of I do it, if you do this exercise, it will be better. Okay. That's why intentionally I have kept this blank. For example, digital arithmetic instruction. Add, sum, mul, and mac. So since 2 bits are kept for the actual instruction, so add, sub, mul, mac. Mac means what? Multiply and accumulate. These are useful for DSP kind of operation. Because in DSP operations, we deal with the convolutions or Fourier transforms. In convolution is basically what? Summation of the multiplications, isn't it?
Yes, sir.
So it's math. And also in neural network, multiplications and they will be added with that xi into wi summations for I equal to 1 to n. So that's a MAC instruction is very important. Similarly, digital logical instruction is AND, OR, XOR, and NOT, and so on. Similarly, your branch instruction could be jump, okay, unconditionally jump address. Because for jump instruction, there is no question of analog or digital. Jump is jump because instructions memory is same for whether analog instruction or digital instruction. They will be stored in the digital form in the instruction memory. So branch. Similarly, subroutine branch will be jump unconditionally, jump to some address, or jump on carry, jump on zero, jump on negative, etc. So subroutine call, then return, then this kind of things. Okay. So stack pointer, load stack pointer will be under data transfer instruction. There must be a register which is stack pointers. Okay. So machine control instruction is simple halt. So these are the type of instructions you you have to design the instruction set based on this because your code is only 8-bit. Out of that, 1 bit is gone for determining analog or digital and rest at this. So this moment you have to select the instructions. I'll give him some hints. Then you must have to follow these steps to be followed for designing a RISC processor. So same concept will be applicable for designing an AD RISC processor as well. So determine the structure of each instruction or instructions format. For RISC architecture, all instructions should be of same length. This includes size of the instructions, including opcode, addressing modes, and I have already decide type of instructions. You decide how many types of instructions. Like here I have mentioned this type of instruction like digital analog data transfer and so on. So here I have written in the algorithmic form. So first determine the structure of each instruction and instruction format. Then decide the type of instructions. Then design the instruction set. So once you get all these things, okay, like what is the format of the instruction, then what are the addressing modes, then what are the types of instructions. So from this information, you design the instruction set. That means you form this table. Okay. And from the instruction set, you can get information about a number of general purpose registers. So here, number of general purpose registers, we have determined that it will be 32. Okay. So since there are 32 registers, if we choose, that means the code for each register will be 5-bit. Okay. So from the instruction set, draw the schematic of the processors. In the schematic. And in the schematic, draw all the control signals. So up to 5 now you understand. The rest again, once we'll cover that. So from this step 1, we have formed the instruction format, size of each instructions. Then from that we can determine what are the memory sizes, different memory, analog, digital, etc. The next step is determine the addressing modes, type of instructions, okay, And then you determine, once you form this table, you will determine the total instruction set. That's the most important part of the design. Once this instruction set design is complete, then we can go for a schematic diagram. Now, one thing I'm telling you, that a few days back I was taking an interview for a Pune-based company, and they are quite famous for VLSI design. So they are with me. Many of my friends were also there, my ex-friends, and the performance of West Bengal students. Few students were there from various colleges of Knockout. It's pathetic. In fact, I was feeling so same. They came forward to console me. And finally, after the interview, I had to hear that we understand it is the present condition of the state. That's why I'm just cautioning you. The basic problem, like if I don't say the problem, perhaps you won't be able to understand because it's very much relevant with the design. Here, but the students from South or from Maharashtra or from Punjab or Delhi, when they appear in the interview, they are completely prepared and they know, because you have to understand what do we mean by VLSI. Only knowing few tools, or that too again in the namesake, doesn't help, because unless you have the domain knowledge, what will you do with the tools, like let's say you can handle some tools or you can write codes in Verilog. That is nothing, in fact. That is a bare minimum. If a doctor tells that I know how to use the stethoscope, it doesn't make any sense. You have to know how to use the stethoscope. That's a bare minimum, in fact. But major thing, you have to know the subject, because we do what? When you talk about VLSI design, this is not in air. VLSI design for what? What design you are going to do? Either it will be for communication applications or signal processing applications or for some computational applications. Various applications could be there. So you must have to have the domain knowledge. If you don't have the domain knowledge, for example, if you don't know the architecture of the AD processor, and you know all these languages, tools, etc., what will you do with that? Okay, so these things, keep in your mind very clearly. The objective should be very clear. Because unfortunately, they are in the interview. Not a single students from Bengal was selected. Not a single. And same thing. In previous also, in 2-3 interview boards, I was there. Since I was not very well, I had to take it in the online. They arranged for it. And my friend, he's in Hyderabad. He's having a very big company. He's the owner of the CMD of that company. He also asked me if I can refer some names. And here, in fact, now they understand the students from Bengal means either from JU or from B college, like IIST, or from Durgapur. You have to come out in that stage. Okay, that's why very clearly when you know some subject or study or that, not like a blind man, your objective should be clear, like what you are going to do. Anyway, so since I'm telling Arijit, since you are involved in this project, and study thoroughly and try to understand what we are going to do. Okay.
Yes, sir.
Anyway,
Yes, sir.
having said that, let's come back to the schematic. So I'm assuming that we have designed the instruction set. Okay. And to get the instruction set, we followed 3 steps. What are the steps? Number 1, we have first got the specifications, like means what are the specifications? We have to design a 32-bit processor. Our operand field will be 24-bit and opcode will be 8 bits. It's an AD processor, so that's why 1 bit is kept for this, and rest of the bits are for actual opcode field. So then we have determined the addressing modes and type of instructions. Then we have selected how many bits are forward. We understand that since there are 4 addressing modes, there are 2 bits, 8 type of instructions, 3 bits. So we are left with only 2 bits out of 8 bits in the opcode, and these 2 bits are for actual operations. So then form this table and design the instruction sets. Clear? Now, any question?
Yes, sir. Sir, you told many things regarding the addressing nodes. So, can you elaborate the thing that is point number 7, that is subroutine?
Yes, subroutine means the call. There's a difference between the branch and subroutine. Branch means what? When you execute an instruction, let's say jump to some address. What is the meaning of that? The instruction flow will go to that address, isn't it? Like each time an instruction is executed, the program counter is changed. It points to the next instruction to be executed. In that way it goes. That is a sequential flow. But whenever there is a branch, then the program counter will be loaded with that field, address field, in the program counter. So next instruction will be executed from this. For an example, let's say your current instruction is at 3450. And here, can you see what I am writing?
Yes, sir.
So jump to 0 F4. Let's say this is the instruction. What is the meaning of that? 3050, that is the current location, and here an instruction jump to 0 if he is there. Now can you tell me what is the meaning of this instruction?
3450 is the current location, and jump to 0 if it means the.
So what is the current value of program counter?
Sir, 3450.
Good. So what will be the next value of the program counter?
Sir,
2080.
2080.
So let's say the next instruction is P451, some XXX, some instruction is there. So in 3450, if some other instruction would have been there instead of jump instruction, then after the execution of that instruction, it could have come to 3451, isn't it?
Yes, sir.
But since it's a jump instruction, what will be the next instruction will be started from which location?
Sir, 20FE.
20FE. So you understand what is the meaning of the jump instruction? Similarly, if I say that this is a jump carry to 20FE, what is the meaning of this instruction? What is the meaning?
Sorry, sir, I forgot that.
If the carry flag is 1, then jump to 20FE.
Yes, yes.
Otherwise, come to the next instruction, 30. That is the meaning. Okay?
Yes, sir. Yes, sir.
So previous one was unconditional jump instruction, and this one is a conditional jump instruction. Understand?
Yes, sir. Yes, sir.
Similarly, subroutine is what? If we say Let's say this instruction is, what is the meaning of this instruction? Let's say call 20FE. What is the meaning? You know, in high level language, when you write the program, do you know C?
Yes, sir.
The function call you must have encountered.
Yes, sir.
In function call, what happens? When you call a function, it go to that functions for execution.
Yes, sir.
You just pass some parameters, and once that execution of that function is over, it comes back.
Yes, sir.
So here also, when you do call 20FE, so it will go to 20FE. Then you can ask me, what is the difference with branch? Branch also could do the same thing. No, the difference is branch instruction doesn't have the ability to come back. Okay, but here, where it should come back, once this call instruction, where 20FE onwards some instructions will be there. Once they are over, then there must be an instruction that is called return. Once this return is encountered, then it will come back to which location?
Sir, that is 3451. The next
3451. So that means the branch and call instruction, you understand the difference?
Yes, sir.
So this call falls under subroutine. Okay, and mind that. So under these subroutine instructions, the call is there, but to execute the call properly, there must be a provision to return back, and that is done by an instruction called RET, R-E-T normally.
Yes.
So that is the basic difference between branch and subroutine instruction. These are very often asked in the interview. There's a fundamental difference between branch and subroutine. Okay, so return address means what? It has to remember the return address. Return address of the program counter. That will be stored in stack.
Stack, yes.
Okay?
Yes, sir.
Is all right now?
Yes, sir.
And machine control is like halt instruction. Like unless there is a provision to stop the computer, it will keep on executing the instructions, isn't it?
Yes, sir.
Like something will be there in the memory and that will be interpreted as an instruction, whatever garbage is there. So that's why there must be an instruction to stop the computer that is called halt instruction. Typically, this is the
HL.
okay. So this kind of instruction, halt. Another machine control is what? Let's say if there is an interrupt. Okay. Interrupt could be hardware or software. So if there is a hardware interrupt, means some external device wants to pay attention of the computer, CPU, it gives a signal here. And CPU, after receiving that signal, it allows the processor to go to a particular location.
Yes.
So call on interrupt. Let's say this kind of instructions. Call interrupt to some address. That means, so this call will be, if interrupt is there, then only it will go to a particular address. So it is a kind of conditional, isn't it? So if there is an external interrupt, then only it will go to a particular location. And of course, there must be a return to come back. Okay.
Yes.
Internally, another kind of thing, software interrupt, is done by some watchdog timer. Watchdog timer is nothing but a registers whose value will be decremented after execution of each instruction. Okay, you can set the value accordingly. And when that value will be 0, or from 0 if you start, if it attains a particular value, then your CPU will go to a subroutine. And where it will go, that can be indirectly done by setting a register contents with some value. Okay? These are
Yes,
called
sir.
software interrupts. So these are very important for executing the for multitasking. When a number of tasks are executed by CPU, then some time is allotted for each of the tasks. So each task, okay, when it executes after a finite interval of time, it will go to the next one, then next one. In a round robin fashion, it will do. Like in your PC, when you handle a number of tasks are getting executed. You don't feel it because it is being done so fast, but it shares the processor time. Okay, these are done by the watchdog time. Anyway, to design this processor first, I'm not using all these things, but definitely this interrupt will be there. That task I have given you to design the instructions, and if you can do these things, I'm telling you, you will really learn this RISC architecture, and then I will talk about your ARM processor, which will be very easy to understand it. So my tips will be, whatever I have told so far, you go through the websites of different processors like Intel, Motorola, Texas Instruments, and DSP processors and see their instructions. Just don't you don't have to read everything. You just go through their instruction set. And once you understand the instruction set, you'll understand their architecture. And getting all this, consulting all these things, you fill up this. Okay, this slide where I've just given example for only one instruction, but the rest of them you have to do it. You do it. Okay, so that will be the first phase of your design of instruction set. And once your instruction set design is complete, then you will go for the processor design. Here, I've tried to do it in a very simple way so that you understand the essence of AD processor. Okay, before I go through this, let me ask you, do you have any question?
No, sir.
No, sir.
Caprio, do you have any question?
Sir, I will have once I start to write the instruction set. So let me go through that.
First here, we in the first slide we discussed about how many memories we have. We'll have program memory, digital data memory, and analog data memory. And we have 5 buses. So let's say here, analog data memory we have kept at the left hand side bottom. Can you see?
Yes, sir.
Then a digital data memory in the right hand side bottom. Can you see that?
Yes, sir.
And then we have the instruction memory in the middle left, the left hand side. Okay. Can you see the instruction memory?
Yes.
Yes, sir.
Okay. So these 3 memories we have placed. Now we'll place the buses. So for instruction memory, we have the instructions memory or program memory data bus and program memory address bus. Can you identify them? For instruction memory, for memory you have to give address and you will get the data from the memory. Because memory doesn't understand whether it is instructions or data. With respect to memory, everything is data. Okay? We interpret If it comes from the instruction memory, it has to be interpreted as the instruction. And if it comes from the data memory, we will interpret it as data. So can you see the corresponding buses of the instruction memory?
Yes, sir.
Two vertical buses near instruction memory. One is the instruction memory address bus or program memory address bus. Another is the instruction memory data
Program
bus.
memory data bus.
Okay. Now, instruction memory address bus, what should be the size? What should be the size of the instructions memory address bus? I've already told.
The
Look at
24-bit.
24-bit. Good. And data bus, what should be the size?
32-bit.
32-bit. Good. Now, address bus would be unidirectional. Listen. But data bus will be bidirectional because data could be written onto the memory. Sorry. Data could be written or data could be read. As first the program has to be loaded onto the instruction memory and then it will be fetched one by one. So it is bidirectional. But address is always unidirectional. Is okay?
Yes, sir.
Now how the address is coming to the instruction memory? Through which buffer address is coming?
Sir, can you repeat the question again, sir?
In the diagram is there. You just look at it. PMAR. Can you see that? It
Yes, sir.
means
Yes,
program
sir.
memory address register. Okay. So it is connected to what? Program memory address
Yes,
bus.
sir.
Okay. No, because address is
Yes, sir.
now. What is the size of this PMAR? What is the size of the PMAR?
32-bit.
How come it will be 32-bit?
No, sir. It is 24-bit because it is just with
Exactly.
program memory address bus.
Exactly. It is 24-bit. Now here, the control signal, extreme left side, that is the signal is the clock. Because all the operations are synchronized with the clock. Okay? And the symbol of the clock is like a triangle.
Yes,
Can you see
sir.
that? Hmm?
Yes, sir.
On the top of PMAR, in the left hand side, there's this clock. Okay. Then I stands for input enable, that is the control signals. So when I is on means high, and at the leading edge of the clock, then whatever is placed in the bus, in the address bus, that will go into the PMAR and will be latched. That's a simple thing. Is okay?
Yes, sir.
So PMR is a 24-bit register, and register is nothing but bar and write bar signals will be there. That is there here. This hash read and hash write means read bar and write bar. So memory gets the address and appropriate signal, either read bar or write bar. If read bar is low, then write bar should be high. That means data will be read from. And once this address is given and read bar is low, the data in the instruction memory will be placed onto the data bus. Or data can be written onto the memory by keeping the write bar is low and read bar is high. That's why it is bidirectional. Is it okay?
Sir, it has been written over there 33. What does it mean? Does it mean it is written over there 32?
Your voice is not coming clear. Please tell.
Sir, I'm saying that 32 is written over there. What does it mean?
32 means 32-bit size. The size of the data bus is 32-bit. Since each instruction is 32-bit, 32 in bracket means this bus size is 32-bit. Instruction memory, each location is how many bits?
32 bit.
32 bits. That's why this 32 bit at a time goes to this bus. So bus will be also 32 bit. That's why in bracket 32 is written.
Okay. Yes, sir.
If not written, you can just
Yes, sir.
it's 24.
It's written 26.
24. So this is the instruction. So instructions will be stored.
24.
Yeah, you can say that is the code. Now we come to digital data memory. What you can see, you just tell me what you can find surrounding digital data memory. What is coming, a vertical line, then a horizontal line. What are those?
Sir, horizontal line is digital data memory. Digital data memory data bus which is 32-bit.
That's 24. Okay, fine. Same thing, read bar, write bar, and this. So here, whenever OE bar is high, then directly the contents of digital data memory address will be going to the digital data memory. Right? Okay. So it's a bidirectional. You must have noticed that digital data memory, the bus is bidirectional, the data bus. Now for analog data memory, where it is and what are the lines?
That is analog data memory data line.
Okay, analog data memory data lines, right. And address will be digital, isn't it? Because address has to be given in the analog data memory. So what is the size
Yes, sir.
of the analog data memory address register? How many bits?
Sir, 24 bits, sir.
Yes, 24 bit. This is a 24 bit. 24 bit digital values will be there. So this for addressing. How the analog memory functions? Analog memory, you have to provide the address in digital form. And here read bar, write bar I have not shown. When you get this diagram, you can complete that by showing read bar and write bar. Okay. In the analog data memory. and then analog data will be coming in or will go into the memory from the analog data line. So one line is there. Okay, you understand? So analog data, the sample data will be coming here. Now this analog data, if you want to convert it to digital, there is an A to D converter at the top. Can you see?
Yes, sir.
And this A to
Yes,
D
sir.
converter, the output of the A to D converter is the digital data.
Yes, sir.
And this digital data can be stored into digital memory.
Yes, sir.
Okay. Or it can be used for other purposes.
Yes,
Okay.
sir.
Or even digital data, what is there? If it needs to be converted to analog, there is a digital to analog converter. Can you see that at the bottom right?
Yes, sir.
Yes, sir.
Now you can ask me, what is the need of this digital to analog converter? Now let's say this processor will be used for your music system. Okay, after processing all these informations and all, can you listen this digital data? When you listen to music, definitely this is analog, isn't it?
Yes, sir.
So that's why D2A converter is there. It's a complete signal processor. So I just kept this thing DAC and ADC, keeping all possibilities. Okay. So I suggest you go through this architecture. Okay. So step one, you have to design the instruction set here. For that, you have to consult various architectures. So 32-bit RISC architecture, you just consult from the net. Okay. The Intel or ARM processor. You don't have to understand all these things in the ARM. I will discuss later on. You just go through the instruction set of the ARM, okay? Or some Intel processor, RISC processor, and you just design your instruction set. It's only for understanding. Once you will be able to do that thing, then I'm sure that will be advanced a lot. Then you will try to map this architecture, what has been done, and just lays down. If there is any confusion, you can ask me in the next class. Okay, or point down 1, 2, 3 that way in the WhatsApp message. But I will not be able to see all this. But definitely in the next class, I'll be addressing those queries and all this. So far is okay.
Yes, sir.
You must
Yes,
have
sir.
you must have noticed that here, among in all these registers, some control signals have been given, and most of the control signals are input enable and output enable. Because data will go into the registers or data will come out of the registers. That kind of. Except the PC. In the PC, there is one signal for increment, INCR. Because after the execution of each instruction, PC will be incremented by 1. So that's why INCR signal is there. Once this is given, the PC will be incremented by 1. Okay? So
Yes,
you
sir.
try to understand why these control signals are required and what is happening for each of these control signals. How this. Okay. So for first, once you complete the instruction set, then you analyze for each instructions what are the different control signals given and how the instructions are executed. Okay. Once
Sir, should we design ADC? What will be the speed of the ADC, sir?
no, you don't have to design right now ADC. You have to do it
Okay.
later on. Right now, whatever I said, you do only these things. Okay.
Okay. Okay. Okay.
Definitely, DAC and ADC you have to design later on. Well, we understand that here is a 32-bit like ADC has to be designed because the output will be 32-bit. very high precision ADC here. Similarly, DAC, 32-bit data to analog signal. So we'll do that step by step. So our approach will be top-down approach. First, we understand the overall architecture.
Okay. Another thing, sir, we just so what will be the sampling frequency? We need analog signal to store in analog memory.
No,
Sir.
this is not fixed. This depends on
Okay.
in which speed we'll be working. What are there are various issues on that. Okay.
Okay.
The
Okay.
signal, what kind of signals we are handling with. For an example, if my signal, this architecture, this processor is going to be used for 50 megahertz signal, then sampling should be at least 100 megahertz.
Yes, sir.
So it is like that. So for an example, when you go to the market, let's say you are going to
Okay.
buy a car, do you
Yes,
feel
sir.
that capability of all the cars are same?
No, 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 no.
So it depends on, we say that this one, this 1000 cc or 800 cc, etc. So depending on that, that means the engine performance, many factors are there.
Yes, sir. So that designing this processor, up to which frequency we can handle it, that should be kept in mind or not, sir?
Yeah, that will be definitely that has to be mentioned. But here first our understanding is first let's try to understand the architecture first, how we are going to do
Okay,
it.
okay, okay. Sure,
And
sir.
once the design of the architecture is over, then we'll just think, okay, this will
Oh,
be
oh,
applicable for what kind of application, what kind of signal processing applications.
sure, sir. Sure.
So
Okay.
understand?
Yes,
And
sir. Yes, sir.
another thing I would like to tell all the students, FPGA as on date, we are using it for basically simulation purpose, for validation. Okay. The architecture, processor and all, that will have to be in the ASIC. There is no other alternative. Okay. FPGA mostly we are using it for validating the architecture. But to get the desired speed of the processor and all, we have to go for the processor architecture. Okay. And that's why there's a limitation of the FPGA as the cost is very high, very high. So for consumer applications, so far, FPGA is still now not in the market. So another thing I would suggest to learn the language which is called Verilog AMPS or VSDL AMPS, that you have to learn, which takes the mixed signal processors. So this is an example of the mixed signal processor. Okay.
Yes, sir.
And what are the applications? The applications are, in one hand, it is a DSP applications. In other hand, it is an application for artificial intelligence. I'll show you. Next day when we'll discuss this analog, just a minute, it has come. Then we'll see how this, and concepts of analog circuitry should also be in the fingertips. For example, here I've given analog AU, and below that there is a flag. Can you see that?
Yes, sir.
Now, flag for what? This question you have to ask by yourself, you. Analog AU stands for analog arithmetic unit. I have not written analog ALU. Have you noticed that?
Yes, sir.
Yes, sir.
Why not analog ALU?
Sir, logically, we can't perform.
Yeah, because logical operations are only on digital data,
Yes.
like OR and. Have you ever heard that analog OR operation, analog AND operations? It's meaningless because analog is not discrete; it's a continuous kind of a thing, and there are various levels. When we talk about digital, there are only two levels, 0 and 1, distinctly. So each bit consists of 1 0 or 1. But here, is the resolution depends on, like, for example, a 8-bit A to B converter. There could be 256 levels. Or 10-bit A to B converter, there could be 1024 levels. So there is no question of your logical operation. So that's why it is AU. Then why flags? Flags means, let's say, zero flag or negative flag. Let's say there are two flags, just for the sake of understanding. Zero means if the operation of addition or subtractions or multiplications, if the result yields a zero, then a flag will be set to 1. Of course, the flag is digital flag. So how this result, if it is zero, this should be converted to this? So here you have to understand the basic analog circuitry clearly, how the additions are performed, how multiplications are performed. So this could be done by the operational amplifier.
Yes, sir.
Secondly, the Smith trigger. Any raw signal can be smoothed by Smith trigger to two levels, 0 and 1. So these are very tricky and interesting uh, to understand this analog circuitry. I can suggest one book. There's a book. No, I don't. I'll just tell you in the next class. Analog signal processing. You can study that thing. Okay.